So welcome to the lesson for 4.1, the inverse trig functions. We've talked about inverse trig earlier this semester. Basically, an inverse function undoes what a function does. So, for example, suppose we're talking about a function whose input is the set of people in the United States with social security numbers, and their output is their social security numbers. So don't try to steal my social security number right here. But for instance, if we say Matthew Rodalowicz is the input and his social security number is 111111111, right? So we'd say f of Matthew Rodalowicz is 111111111, right? So that would be a function. Because for every name we give it, if we say f of Donald Trump, then Donald Trump has one social security number. F of Barack Obama, the function would give back a social security number. No one that has a social security number has two social security numbers. Every name of that we input would give it back one social security number. The inverse would be to say, suppose I give you 1111111, who does that belong to? So the inverse of f inputs social security numbers and outputs the names, right? So keep in mind what a function input is versus what its output. An inverse interchanges those, and we've seen that earlier this semester. So the inverse of a function reverses what the function does. Furthermore, if there is a one-to-one correspondence, we say the function is invertible. So going back to the name and social security, there is a one-to-one correspondence. Every name pairs with one social security number. So if we switch that, the social security number will always pair with a name. However, if I were to say, here's a function, we're going to give it a name, and then it outputs the last, if we give it a name and it outputs the person's favorite color, so we could say Matt, and my favorite color is blue. And maybe we could say Jim, and Jim happened to have a favorite color of blue. So that relationship is functioning because every name pairs with their favorite color, and that's what the definition of a function. However, name and color, Matt, Jim, both pairing with blue. Well, now if we say who has a favorite color of blue, we're getting multiple outputs, Jim, Matt, and probably many, many, many other people have a favorite color that's blue as well. And that's not the definition of a function. Given one input, it must pair with one output. So in that relationship, name paired with favorite color does not form a one-to-one correspondence and therefore would not be invertible. So we're going to look at a couple functions in a minute. One that's forms a one-to-one correspondence, and we can confirm it graphically, and then a couple that are not in the one-to-one correspondence, but how we deal with that in mathematics so that they do become in a one-to-one correspondence. Consider f of x is 2x. Is that a one-to-one function and therefore invertible? Well, you should recognize that f of 2x is a linear function, has slope of 2, and a y-intercept of 0. And no matter what x you give it, no matter what input you give it, it'll pair with one y. So for instance, if x was the value 3, y would be the value 6. So if this was 3, that would pair with 6. And there would be no other value that would give you 6. The only way to make 6 in this function is to input 3. And that's true for all numbers. So for instance, if you wanted to make the number -2, you look down here at -2, there's only one x value that would do that, and we can see that that's -1. So ponder that a little bit, but in general, from a graph, we can tell that a function is 1-to-1 if it passes the horizontal line test. If you can imagine drawing horizontal lines through the graph and there's only one intersection, then your function is in a 1-to-1 correspondence. So it passes the horizontal line test. Therefore, yes, it is a 1-to-1 function and therefore invertible. If we now consider the quadratic function f of x equals x squared, which is a parabola, we can immediately apply the horizontal line test to see that it is not in a 1-to-1 correspondence. So for instance, if x is 2, the output would be 4. However, if the x was -2, the output would be 4. So that's very similar to the question, Matt, favorite color? Blue. Jim's favorite color? Blue. Yes, give me a name. It gives you one output. So in a quadratic function, 2 squared, 4. -2, -2 squared, 4. But if we now interchange those, what inputs give me 4? Well, you actually have two values, both 2 and -2. So the quadratic function technically is not invertible. However, here's a little tidbit, a little enrichment. If we restrict the domain of the function to greater than 0, so if I were to cut, if I could imagine cutting out half the parabola there, just everything less than 0, and now we only consider values of x of 0 or greater, then we would have a quadratic function that is invertible. It would definitely pass the horizontal line test. And for that reason, this explains why in mathematics the square root of 4 is 2. So I don't want to get too bogged down or make this more confusing to you than it needs to be, but that symbol, the square root symbol, has always been taught correctly to represent the positive value only. And if you ever remember being in elementary, middle school, high school, and you've had the question about, well, aren't there two square roots of 4, both 2 and -2? You're absolutely right. But symbolically, and for niceness, if you will, for function's sake, mathematics insists it must be that the square root symbol means to only give back the positive answer. So that's that. I don't know what else to say. It's just a little background knowledge about maybe some things you previously thought about in terms of square roots and stuff, and just trying to give it a little more depth here. But now let's enter our trig world, if you will. So now let's consider f of x is the sine of x. So I sketched a graph. Remember, here's one fundamental curve. Probably could have sketched that a little bit better, but it has a maximum of 1, a minimum of -1. So here's our fundamental cycle, and this should arch curve down a little bit on its end there, not look like it's going to infinity, but so be it. I also put in a cycle or a partial cycle for values less than x, for values of x less than 0. And clearly we can see that this graph is not 1-to-1. Okay, clearly it fails the horizontal line test. So for instance, at pi over 2, you get a maximum value of 1. We know if we look backwards, or if I think about the unit circle, if I traveled clockwise, negative 3 pi over 2 would also give me a value of 1. Or if I traveled an additional 2 pi radians, 9 pi over 2 would give me a value of 1. So there are multiple angles of rotation that have a maximum value of 1. Again, going back to the Matt and Jim, pi over 2, sine of pi over 2, 1. Sine of negative 3 pi over 2, 1. Sine of 9 pi over 2, 1. Give me a bunch of names. They all have a favorite color. Well, give me a bunch of angles of rotation. They'll have a maximum of 1. So when I switch that, it's not going to be a 1-1 function. However, much like the parabola in the previous example, in mathematics, we restrict the domain so that it does pass the horizontal line test and therefore is invertible. Can you see where we might restrict the domain? And I've played this game in class before, and there's actually different answers. But the most common answer, and whether it's what you chose or not, it is what mathematics has decided, or mathematicians has decided to define as the interval right there from negative pi over 2. So I just highlighted it. If we just had this section, if we restricted the domain from negative pi over 2 to pi over 2, the graph would pass a horizontal line test and therefore be invertible, and therefore its inverse would function. So what I've done now is tried my best to give a little backstory to bring back again what inverse functions are and to give a little conceptual understanding about restricting domains for functions that fail to be one-to-one. But with no further ado, we're going to define the inverse of sine, cosine, and tangent functions right now. And before I go any further, I just want to remind us that the sine of an angle of rotation is the y coordinate where the terminal sine intersects the unit circle. So in layman's terms, pretty quickly, the sine given an angle of rotation, you output the y. Similarly, for cosine, given an angle of rotation, you give back the x. And for tangent of an angle of rotation, you give back the ratio y to x. Now let's go back to sine. Angle of rotation is my input, output is y. And after we restrict the domain, it is one-to-one, so therefore we can invert them. So the sine inverse function, actually you are going to be given a y coordinate and you're going to now return the angle of rotation. But as we saw in that restricted domain, that angle of rotation must be between negative pi over 2 and 2. So what I've written right now, and what the textbook has written, is basically the inverse function of sine, which also is written as arcsine. These are literally just different notations, two ways of writing the same exact thing, and they're interchangeable. I mean, they're used interchangeably without reason. So just be comfortable with knowing two ways of saying the exact same thing. Okay. That means that's really equivalent to saying that the sine of y is x. So I'm going to explain this in a few moments on another slide, but when I look at what I've just written, sine of y is x, I get nauseous myself with all these y's and x's, and that's why I want to go back to say, to remind you that the sine function takes an angle of rotation and gives back a y coordinate. Therefore, the inverse is going to take that y coordinate and give back an angle of rotation. Again, it's very confusing with x's and y's all over the place, but if you listen to my words and not necessarily what is written in textbooks and what we're writing right now, you'll find success in this. And I'm going to do that in just a few slides, so hang tight. I'm just kind of dropping it at you right now. While we're in here, I also put in the definition for the inverse cosine. Oh, actually, let me stick here. Forgot I did this. So this is just a little addendum. So we know that the sine of pi over 6 is 1/2. What I'm arguing is we can rewrite this as pi over 6 is the inverse sine of 1/2. Or pi over 6 is the arc sine of 1/2. Right? So the original line up here, I really need to get a pointer for this screen, but in the original line up here, the sine of an angle gives you back a y coordinate, and that's the sine function. So now the inverse interchanges those. So the inverse sine takes a y coordinate and returns the angle. So going back to that previous definition, try to internalize the word angle and y intersection or x intersection along the unit circle. But sine and cosine and tangent input an angle. The sine outputs the y intersection. The inverse sine inputs a y intersection then and gives you back the angle. And similarly, for cosine or arc cosine, the behavior is the same. You're returning back an x intersection when you input an angle of rotation in cosine. So therefore, the inverse cosine is asking you to find an angle of rotation. And the one thing to notice here is that angle that you return is not from negative pi over 2 to pi over 2, but instead it's from 0 to pi. And the explanation of that is very similar to the explanation that I showed with the graph of sine. It has to do with limiting or restricting the domain. But if you restrict it between negative pi over 2 and pi over 2, you don't capture all the values. Actually, you don't even form a one-to-one function, so it's not helpful. So I suggest you read the book or do some additional research yourself if you're interested in more information. But for those of you who just want to get to the facts, the inverse cosine will always be a value between 0 and pi. You're returning a quadrant 1 or a quadrant 2 angle. For tangent, you're returning a value similar to sine between negative pi over 2 and pi over 2. Okay. And the same argument is made there. It has to do with restricting the domain in order to have an inverse function, a one-to-one function. So that's a lot of the background, the understanding, the conceptual part of it. To actually do these questions, I think is pretty straightforward if you have your unit circle. So at this point, if you don't have your unit circle ready, pause the video and get this, get your unit circle by your side. That's all the conceptual part. Let's actually do or evaluate the inverse trig functions. So if we're asked to find the inverse sine of square root of 3 over 2, I like to say, let's start with the sine function. Since this pi over 3 is the square root of 3 over 2, then pi over 3 is the inverse sine of square root of 3 over 2. We're just interchanging. Let me back up there. So we're just interchanging our inputs with our outputs. So as written, it's asking us, hey, what angle of rotation has a sine value of square root of 3 over 2? But that angle must be in between negative pi over 2 and pi over 2. So you look at your unit circle from negative pi over 2 to pi over 2, and you say, hey, at pi over 3, you have a sine value of square root of 3 over 2. Therefore, your answer is square root of 3 over 2. We're asked to find the arc cosine of negative 1/2. So I begin by writing saying I like to think of what angle of rotation has a cosine of negative 1/2, and reminding us on that definition before, that angle of rotation must be between 0 and pi. Well, immediately, if it's negative, I know it's in quadrant 2. And looking at my unit circle or recalling my unit circle from memory, I know that it's 2 pi over 3. So we have it. 2 pi over 3 is the arc cosine of negative 1/2. So I'm just emphasizing what's written on the previous page there. Let me back this up here. All I'm emphasizing is that your angle must be between negative pi over 2 and pi over 2 for inverse sine, and 0 and pi for inverse cosine. So that's important. Actually, I'll let the video run here. So to find the arctan, the first thing I wanted to recognize is that I needed to rewrite this by rationalizing. So that was my first step. And now I'm going back and saying, I need to find an angle of rotation whose tangent is square root of 3 over 3, and that angle of rotation has to be between negative pi over 2 and pi over 2. So the answer to that is pi over 6. Therefore, pi over 6 is the angle is the arctan of 1 divided by the square root of 3. And just reminding you what I said, that this angle, this y value, must be between negative pi over 2 and pi over 2. So the inverse of cosecant, secant, and cotangent. Pretty nice to, easy to memorize, I should say. We know that the cosecant function is the reciprocal of the sine. So without proof, just stating the fact here, the inverse cosecant is equal to the inverse sine of 1 over x. You reciprocate your input, if you will, okay? So the cosecant, the inverse cosecant becomes inverse sine, and what's inside the function, what's inside the inverse cosecant reciprocates as well. So you're basically reciprocating both parts. That's not a proof. It's a way to memorize how to apply the definition. And the same is going to be true for the remaining quotient functions. The inverse secant of x is equal to the inverse cosine of 1 over x. Again, you are a shortcut trick here, but you're writing the reciprocal of secant as cosine, and you're also reciprocating the inner part of the inverse secant. And lastly, for tangent, for cotangent, it's a little bit messy. I would not recommend memorizing this. Just be able to apply this in different cases. So if your original x is greater than 0, then the inverse cotangent of x would become the inverse tangent of 1 over x. However, if your original input is less than 0, then the inverse cotangent is written as the inverse tangent of 1 over x plus pi. And lastly, if x is 0, then the inverse cotangent of x is strictly just pi over 2. There's nothing to compute. You just write pi over 2. So applying those, I immediately change the inverse cosecant to inverse sine, and I'm going to reciprocate the inside. And now I practice what came before this. How do I find the inverse sine of square root of 3 over 2? Well, I think to myself, what angle of rotation between negative pi over 2 and pi over 2 has a sine of square root of 3 over 2? And the answer is pi over 3. Therefore, our final answer to all this is pi over 3. Again, my first step here is to invert or to rewrite the inverse of secant as the inverse of cosine, but I need to reciprocate the inside value of negative 2 to negative 1/2. And at this point, now I ask myself, this means to find the angle of rotation between 0 and pi whose cosine is negative 1/2. Since the cosine of 2 pi over 3 is negative 1/2, I have my answer, 2 pi over 3. Last, find the arc cotangent of 1. Immediately I rewrite it, applying the definition. So my input is 1, and when I look back at the definition above, if your input is greater than 1, if your input's greater than 0, we write arc cotangent as arctan or tan inverse, and we invert 1, but the reciprocal of 1 remains 1. And now I ask myself, what angle of rotation between negative pi over 2 and pi over 2 has a tangent value of 1? And using your unit circle knowledge, we know that that angle of rotation is pi over 4. Okay. A few last examples to compute here. This is really just skill working, making sure you're paying attention to inverse trig versus your trig functions, okay? So when we compute this, look at your inside function. You're going to do your inside first, and then your outside function second. So inside, we have the sine of pi over 2. Sine of pi over 2. That's a trig function. So we have an angle of rotation, pi over 2. The sine of pi over 2, the y coordinate, is 1. Now we work on our outer function, inverse tangent. So I need to think of a tangent. I need to think of an angle of rotation whose tangent is 1. Right? So pay attention to trig functions versus inverse trig functions. And I know this to be pi over 4. That's it. That's our final answer. The inverse tangent of the sine of pi over 2 is pi over 4. That is a mouthful. This whole section feels like a mouthful of pi's and inverse and function and tangents, cotangents. One more example here. And I have a typo on this. All right. So there is a typo on this example. Typo. Please fix your paper. I started to do this and I said, wait a minute. I didn't type the question I wanted. So ignore this for a moment. That's the question you want to be able to answer. The sine of the inverse cosecant of negative 2. So we'll start on our inside function, which is the inverse cosecant. A few steps to do here. So inverse cosecant. Well, first I'm going to rewrite it as inverse sine, but I will then need to reciprocate the inside. So as I just said, inverse cosecant becomes inverse sine, reciprocate the inside. And now I got to say, all right, inverse sine means I need to figure out an angle of rotation between negative pi over 2 and pi over 2, whose sine is negative 1/2. Well, the sine is negative in quadrant 4, which implies that we're going to rotate clockwise pi over 6 units. And since we rotate clockwise, the angle of rotation is negative. So ponder that. You should have a good understanding of all the lines and all my reasoning here. But so far, the inner part of this expression is going to be replaced with negative pi over 6. And now we're asked to compute the sine of negative pi over 6. Which means rotate negative pi over 6 and then take the y value. In that case, it's negative 1/2. The last example you need to do is write an expression for this composition expression. We're given the cosine of the arcsine of x. So again, when I start on my inside, I want an angle whose sine is x. That's strange. It's unknown. Up until now, we've been doing it with numerical values, but we're about to do some algebra writing. All right, so start with your innermost function and read it to yourself. You need to create an angle whose sine is x. This is slightly different than what the book does, but my college professor showed me this, and I've never forgot it since. I think it's a lot easier than applying identities, although if you do look at the book, it's going to show you how to do this using identities. But let's draw a diagram. Let's draw a diagram of an angle whose sine is x. What kind of diagram should we draw here? It's not obvious, but we'll draw a right triangle. Okay, so you start by drawing a right triangle. we need an angle, and now we need to have this model, the sine of theta being x. All right, so here's an angle. Now we want this diagram so that its sine is x. So I'll let you stare at this for a minute, but we're good. We've done it, or I've done it in this time. So looking at that diagram, the sine of that angle is x over 1, which is x. There we go. We have found an angle whose sine is x, or at least in a diagram approach. So what I've done here is to say, let's call that inside expression theta, and arc sine of x equals theta means sine of theta equals x, and we have a diagram that shows that. So from there, I'm just going to play the video part of this. Now, we need to find the cosine of that angle. And we know that the cosine of right triangles is adjacent over hypotenuse. Well, we don't have the adjacent value, but the good old Pythagorean theorem allows us to find it. So when I apply the Pythagorean theorem to the diagram, I end up with the missing side as plus or minus the square root of 1 minus x squared. But in a triangle, you can't have a negative side length, so I just take the positive value, and the cosine of that angle is the square root of 1 minus x squared over 1, which just simplifies to the square root of x, the square root of 1 minus x squared. And that's your video lecture for section 4.1. Have a good night.